Hi everybody! So today we're going to examine some fun experiments you can do with a tourmaline slice. So here is an example of one of the tourmaline slices. These come in a wide variety of colors, shapes, and sizes, however they're all made from natural tourmaline crystals. And as such, some of these have a bit of color zoning, some of them have inclusions, some of them are a bit fractured. So there are some variations here, however, these have all been selected because they demonstrate rather extreme pleochroism. So extreme, in fact, that we're not even going to need a polariscope to show off how crazy this pleochroism is. So this particular slice is a rather deep green, and let's also take a different view of this slice just so you can get an idea of its geometry. We have these available for sale at the eBay store, Snellius Minerals, if you'd like to try out any of these experiments for yourself. And let's start out by going through a bit of background information on tourmaline. When looking at a mineral, it's important to remember some of the basics. So when we have a mineral, it is defined by its chemistry and structure. The chemistry and structure will determine the crystallography we see at the macro scale, as well as the optical properties that we see. Usually, if we can figure out any two pieces of the triangle shown here, we can then also figure out the third because they're all ultimately linked by that chemistry and structure. So our tourmaline is defined by its chemistry and structure. And as you can see from that chemical formula, the chemistry of tourmaline is rather complex. And this is because the tourmaline group of minerals has a wide variety of solid solution series. However, those solid solutions can all occur within a very similar structure. So our tourmaline is a cyclosilicate that has 6-membered tetrahedral rings, and those rings are oriented so that their apical oxygens are all pointing in the negative C crystallographic direction. Once again, if you want to understand the structure of tourmaline better, I'd suggest a website like Mindat. It's going to be much better than any structure model I could try and put together. So that chemistry and structure yields the space group symmetry that we see at the micro scale. The space group symmetry is R3M. And when looking at the macro scale, our point group symmetry ends up being 3M. Let's examine the crystallography of a tourmaline crystal under just normal lighting conditions. So this is a fairly euhedral tourmaline crystal. What I'm going to do is just spin this around a bit so you can get an idea of the shape. You can see the one end of our tourmaline is terminated, whereas the other end is a fracture surface. The tourmaline was growing on something and was broken off from it. So hopefully you have an idea of the geometry of our tourmaline crystal. This view of our crystal is going to be one of the important views. Let's think a little bit about the symmetry we might be seeing with this view. Our point group for tourmaline is 3M. So translating that point group symmetry element means that our C crystallographic axis is going to be a threefold rotational axis, and in a plane perpendicular to that C crystallographic axis, we'll have 3 A crystallographic axes. These A crystallographic axes aren't going to have any symmetry elements themselves, but perpendicular to these axes will be 3 mirror planes. So given the shape we're seeing in this direction, what we're actually looking at is the threefold rotational axis of our tourmaline crystal, and then we're also looking along the C crystallographic axis. So we know our A axes are going to lie in a plane perpendicular to our C crystallographic axis. However, it's easier to spot the perpendicular mirror planes first since the A axes don't actually have any symmetry element of their own. So after spotting the perpendicular mirror planes, we can now add on our A crystallographic axes. And once again, the A axes are a bit weird in the point group 3M as they don't have any symmetry element of their own. So let's now take a different view of our tourmaline crystal looking along the plane of the A axes. And to start with this bit of 90-degree rotation, we're actually just looking down one of those perpendicular mirror planes. We're actually going to have to rotate the crystal a bit now in order to look down one of the A crystallographic axes. And it's also going to look kind of weird because our A crystallographic axes, once again, don't actually have a symmetry element associated with them directly. This is a bit of a weird view, but we are indeed looking down one of the A crystallographic axes. We can then add on some of our other A crystallographic axes to this view. And we know that our C crystallographic axis is going to be perpendicular to the plane of the A axes. Now that we've examined the macroscopic crystallography of our tourmaline crystal, let's go back to the big picture we were talking about before with our mineral tourmaline. The chemistry and structure of our tourmaline also determine the optical properties. Our tourmaline is uniaxial negative, with ranges of values for refractive index epsilon and omega because of the solid solution the tourmaline exhibits. If you'd like some background information on uniaxial minerals, check out the video Optical Mineralogy Uniaxial Materials. Here's an example of the pleochroic end-member colors associated with refractive index omega and refractive index epsilon for our tourmaline. And this example was actually taken from the video Snellius Minerals Linear Polarizers. Some other important tourmaline facts. Our tourmaline has a hardness between 7 and 7.5. The crystal structure leads to no preferential direction of bond weakness, so there's no cleavage in the tourmaline structure. The density of tourmaline is around 3 to 3.25 grams per cubic centimeter. Once again, there's a range in values here due to the solid solution the tourmaline exhibits. Because the tourmaline structure has no center of symmetry, tourmaline is both piezo and pyroelectric, and this means it has some niche industrial applications. Tourmaline further exhibits a wide variety of colors from both the solid solution we were talking about before, as well as additional impurities. And one feature common to many tourmaline crystals are vertical striations parallel to the C crystallographic axis. This is really helpful for orienting even small fragments of tourmaline as long as you can find this feature. So we're going to go examine some of the optical properties of a tourmaline crystal now. However, we should first, of course, mention the optical indicatrix for tourmaline. This is a three-dimensional representation of the refractive indices of our tourmaline. And as our tourmaline is uniaxial, it's going to be defined by two refractive indices, epsilon and omega. Refractive index epsilon is going to be aligned with the C crystallographic axis, and refractive index omega is going to be associated with the plane of the A axes. So for our first experiment, what we're going to do is transmit light through our tourmaline crystal. And unlike many of our other experiments, we're not going to need a polariscope here because the pleochroism of the tourmaline is that extreme. So the light we're going to use in this experiment is just light from a cell phone flashlight, no fancy lighting conditions needed. And because we're not using plain polarized light, the light that's going to be interacting with our tourmaline is actually going to be vibrating in all sorts of different planes. Here we have our tourmaline slice example from earlier. We're viewing light transmitted through the tourmaline slice, and our illumination source is just that cell phone flashlight. And you can see this crystal in particular is a very deep green. If we spin our tourmaline crystal in one particular plane, you'll notice that this green color persists as we rotate the crystal. But if we flip our crystal into a different orientation, what actually happens is all of the light is absorbed in this direction through our crystal. So once again, in this direction, total absorption of light, and in this direction, pretty green. Total absorption of light, pretty green. Let's actually check out one additional orientation of our crystal here. And we can see once again, we have pretty green as long as we're rotating in this particular plane. So this is an excellent example of pleochroism. We're seeing different colors associated with different directions light is traveling through our crystal. Usually to observe pleochroism, you want to be viewing a sample with transmitted plane polarized light. But our tourmaline is a bit special because the absorption of light associated with refractive index omega and refractive index epsilon are different enough from one another that we can actually just see this without needing plane polarized light. Let's go back to the first image of our tourmaline crystal to investigate further. So what we're looking at is a slice of a tourmaline crystal that I've cut very specifically to highlight this pleochroism. And even though I've modified this tourmaline crystal, we've still got some crystallographic clues to help us figure out what direction we're looking at with our crystal. So I want you to notice all the vertical lines that we can see in our tourmaline crystal in this view. Here are some of these lines highlighted in gray to help you spot these in our crystal. And what these are vertical striations that are running parallel to the C crystallographic axis of our tourmaline. That's right, the random bonus tourmaline facts are actually useful. And so once we've identified these vertical striations, we now have an idea of the crystallographic orientation of our tourmaline. If these striations are parallel to the C crystallographic axis, that means we're looking somewhere down the plane of the A-axes of our tourmaline. And when looking down the plane of the A-axes of our tourmaline, we know that we're looking at this view of our optical indicatrix for tourmaline. Because we're not using a polariscope and we don't have any special lighting conditions, this view will allow us to see light both associated with refractive index epsilon and light associated with refractive index omega. Our normal light is vibrating in all sorts of different planes, and so we can't effectively isolate epsilon and omega from one another in this view. We'd need plane polarized light in order to do that. Let's return to our original video clip, and now I want you to think about what we're doing here as I begin to rotate the crystal in this plane. What's actually happening is we're just taking different views, always still down the plane of the A-axes. And so what that means is that we're not really changing our view of our optical indicatrix as we rotate our crystal in this manner. We're always going to see refractive index epsilon and refractive index omega. This is going to change, however, as soon as we flip our crystal viewing down a different direction. So given that the vertical striations on our tourmaline crystal told us the direction of our C crystallographic axis, this 90-degree flip that we just did should mean we're looking down the C crystallographic axis. You can also tell that the shape in this direction is a bit trigonal. This wasn't the prettiest crystal that I cut here. So if we're looking down the C crystallographic axis of our tourmaline, that also means we're looking at this view of our optical indicatrix for tourmaline. And so in this instance, we're only seeing light associated with refractive index omega. Well, what's actually happening is we're not seeing much light at all because refractive index omega is associated with the near complete absorption of light. Our video has one more tourmaline orientation that I want to go through in a bit more detail. From our view looking along the C crystallographic axis, if we flip our crystal 90 degrees, light begins to be transmitted through our crystal again, and we see a deep green color. And following all the different orientation changes of our crystal, we are still looking down the plane of the A-axes. Once again, the striations on the crystal provide a valuable clue to our crystallographic orientation. If you weren't able to follow all the different flips that were going on there, I know it's a bit much sometimes. So as I mentioned, we're once again looking down the plane of the A-axes. However, we have our tourmaline crystal oriented so that the C crystallographic axis is running east-west in this view. Earlier we were looking at it so that it was running in a north-south direction. And so with this view, our optical indicatrix would be oriented in the following fashion. Once again, because we're not using plane polarized light, we are seeing both light associated with refractive index epsilon and refractive index omega in this view. To review everything we just went through, we have taken two different views where we're looking down the plane of the A-axes of our tourmaline, and with these two different views we end up with the same result where we see a dark green color. When we're looking down the C crystallographic axis of our tourmaline, we only see light associated with refractive index omega, and in this case we don't see anything at all as all of the light is absorbed in that view. So let's actually take a look at our tourmaline crystal now using a polariscope. Usually my polariscope setup I have uses an LCD screen as my light source, light diffuser, and lower polarizer. But it turns out in this instance, my LCD screen isn't bright enough to get enough light through our tourmaline. And so what actually works out better in this circumstance is building the little polariscope as detailed in the video Snellius Minerals DIY Polariscope. So what this consists of is a light source that is a cell phone flashlight, a piece of paper that acts as a light diffuser, and two linear polarizers for our upper and lower polarizer. So here we're starting out with our cell phone flashlight and that piece of paper acting as a light diffuser. we can bring in our lower polarizer here, and you'll see the light dim a bit. And now we have a bright enough polariscope to explore some more what's going on with our tourmaline slice. With this setup, our plane polarized light is vibrating in a north-south direction. As we bring our tourmaline slice into the field of view, you can see a dark green color that is similar to what we saw earlier when viewing our tourmaline in normal light. Using the striations on our tourmaline slice, we know that our crystal is oriented in the following manner, and that we are looking down the plane of the A-axis with the C crystallographic axis of our tourmaline oriented in a north-south direction. This also means that we're looking at this view of the optical indicatrix for our tourmaline, and because our plane polarized light is vibrating in a north-south direction, that means that it is currently aligned with refractive index epsilon of our tourmaline. So the dark green color that we're seeing here is the pleochroic end-member color associated with refractive index epsilon. So let's rotate our tourmaline crystal 90 degrees while still viewing down the plane of the A-axis, and you'll notice very different behavior from when we were looking at the tourmaline in normal everyday light. So we're still looking down the plane of the A-axis, however we've rotated our crystal so that the C crystallographic axis is now pointing in an east-west direction, and as such we're viewing this view of our optical indicatrix. Our plane polarized light is still vibrating in a north-south direction, and as such the plane polarized light is now aligned with refractive index omega of our tourmaline, and the complete absorption of light in this direction is the pleochroic end-member color associated with refractive index omega. Let's return to a view where we see the pleochroic color associated with refractive index epsilon, and now let's reorient our crystal so that we're looking down the C crystallographic axis. So we're now taking a look at our crystal along the C crystallographic axis, and that means we're looking at this view of our optical indicatrix. In this direction through our crystal, our plane polarized light will only ever be aligned with refractive index omega. This means we'll only see the pleochroic end-member color associated with refractive index omega, even as we rotate the crystal in this plane. And as such, our tourmaline crystal stays dark even as we rotate it. Yes, the optic axis and the C crystallographic axis are pretty boring. Let's now review the behaviors our tourmaline exhibited while we were viewing it with our polariscope using plane polarized light. When viewing our tourmaline slice along the plane of the A-axis, we can now transition between viewing light associated with refractive index epsilon and refractive index omega as we rotate the crystal. Our view along the C crystallographic axis, however, means our plane polarized light is only ever aligned with refractive index omega, and so we don't see any change in color as we rotate the sample. The tourmaline examples today show us the usefulness of the polariscope. By using our plane polarized light when looking down the plane of the A-axis of our tourmaline, we can isolate light associated with refractive index epsilon and light associated with refractive index omega. This is in contrast to what occurs when we're looking at our tourmaline along the plane of the A-axis using normal light. There, no matter the orientation of our crystal, when viewing down the plane of the A-axis, we end up with the same result, where we have a blend of epsilon and omega. And we end up observing a deep green color. As I mentioned before, the pleochroism of our tourmaline is actually pretty extreme. We get into a unique situation with our tourmaline when viewing our tourmaline with normal light. Because omega is associated with almost complete absorption of light, the deep green color that we observe is almost entirely associated with refractive index epsilon in this case. Our tourmaline is actually acting as a linear polarizer. So for more on that, check out the video Snellius Minerals Linear Polarizers. For a different uniaxial mineral with less extreme pleochroism, looking down the plane of the A-axis while observing our sample with transmitted normal light would result in an observed color that was a blend of the pleochroic end-member colors associated with refractive index epsilon and omega. Only because refractive index omega in tourmaline is associated with near complete absorption of light do we end up only really seeing epsilon in this particular case. Also note that in tourmaline, refractive index omega being associated with near complete absorption of light is only true for certain colors of tourmaline. My goal for our tourmaline slice, however, was to produce a mineral sample that could exhibit pleochroism under normal lighting conditions, so people didn't necessarily need a polariscope in order to actually show this property off. And our tourmaline slice does this job rather well. Looking down the plane of the A-axis, you'll be able to see a beautiful green color in normal light, whereas looking along the C crystallographic axis results in the complete absorption of light. So if you are interested in doing these experiments yourself, you can pick up a tourmaline slice at the eBay store, Snellius Minerals. These tourmaline slices are made from natural tourmaline crystals, and so they are quite variable. However, all of these slices will be able to show off the extreme pleochroism of tourmaline, even when viewing these samples with just normal everyday light. I'll probably have some other tourmaline products up for sale as well, so just make sure you pick the right one for your purpose. So if you have any questions, comments, or specific requests, you can reach us via email at snelliusminerals@gmail.com. Here are the references I used in the construction of this video. I hope that this video was helpful in thinking about tourmaline and pleochroism, and thanks for watching, and have a great day.